Hello, so today we are going to take a look at this problem called longest mountain in an array. And basically the problem is finding the longest mountain subarray in an array, in a given array. And if we can't find such a mountain, we should return 0. And basically what the mountain means here is, if we look at this example, let me just color this. So if you look at this example, we have 8 and then we go down. We have 1, 3, 6, which is going up, and then we reach a peak at 6 and then we go down again. So it kind of forms a mountain there. And so we should return 5 because that's the result, right? That's the length of this subarray, the mountain subarray. And the subarray here, the constraint is that it should be contiguous. And then in the example 2, if you see here, there is no mountain, there is nothing, numbers don't go up and then go down. Basically, they don't reach a peak and go down. And so we just return 0 here. So that's the problem. Now let's see how we can solve it. Okay, so let's see how we can solve this problem. So if we take the example that we had here, which is, so the example that we had is 8, 1, 3, 6, 2, 1, 4, right? So with this example, how can we solve the problem? So we said that the solution is this here, because it goes up from 1 to 3 to 6. So 3, this is 1, and then to 6, and then starts going down to 2, 1, and then it goes up again to 4, right? Maybe this is 4. So, and then it was at 8 before, so it was somewhere here like this. So you can see here the mountain, the only mountain in this array is this one, but this is also the biggest one, right? So one thing you can notice here is, well, what if we just go to the left to find all length of increasing subarrays ending at each point, right? Ending at each position. And so what that would mean is that, well, the longest increasing subarray at 8 is just 0. At 1, it's not increasing, it's decreasing, so it's 0. Up from 1 to 3, the length is 1 because it's increasing from, and then it increases again to 6. So at 6, it's 2. Then it decreases at 2, going down to 2. So at that point, it's 0. So when it decreases is 0, and when it increases, we just add up to the amount it was increasing at before. And then from the right, we can find the decreasing. So from the right, we can find all lengths of decreasing subarray ending at that point. And so at that point, we can just find the peak, which is 6 here, and just add up the increasing portion of the peak plus the decreasing portion of the peak, right? At that point, that's the length of the mountain, and we can just add that up and get the final result, right? So let me try to maybe give a different explanation to make this more clear. So 1, 3, 6. We would have 2, 1, 4. So let's go through this and let's do for the left side. So we start out from 8, so we have nothing before, so let's just put infinity here because we don't know, right? Because we have nothing before. At 1, well, it's decreasing. So here, since there is nothing before it, so it's not increasing, so let's just put 0 actually. Let's put 0. Here it's decreasing, so it's not increasing, so let's put 0. At 3, actually, you know what? Yeah, let's put 0. That's better. So let's put 0 here. Let's put 0, and then from 1 to 3 it increases, right? So we put 1. From 3 to 6 it's increasing, but it was already increasing, so the length of the increasing subarray is 2 here, and then it decreases, so the length here is 0, and then it decreases again, so 0, and then it increases, so 1. And then if we do a similar thing from the right here, but for decreasing, so 4, well, it's there is nothing before, so 0. For 1, from 4 to 1, it decreased, right? And so we will say, so actually, so for 4 to 1, it's from 1 to 4. And so it's increasing. Right? So it's increasing, it's not decreasing. So we say 0. From 2 to 1, right? 2 to 1, it was decreasing. So we have 1. And then from 6 to 2, it was decreasing. So we have 2 here. I know it's a little bit confusing because we are going from the right, but you need to compare this one against this one. That's what we are doing here. So from 6 to 3, sorry, from 3 to 6, uh, it's increasing. So we have 0 here. And then from 1 to 3 is increasing again. So it's 0 for the decreasing subarray. And then from 8 to 1, it's decreasing. So we have the sizes 1 here. And so what we want to find is the peak positions, or the peak positions of the array, which is basically the when both increasing and decreasing portions are positive, right? So let's call this the up, because this is going up and this is going down, and let's call this going down. And so the peak positions of the mountains in the subarray in the array, it's basically I, such that up of I is positive and down of I is also positive, right? So the positions where both up and down are positive, those are the possible mountains. And in our specific case here, it's only for this element that has both positive. All of them have either equal to 0, so this one is equal to 0, so it's not a peak. Here is equal to 0, so not a peak. Same thing here, same thing for all of them except this here. So that's the only peak of a mountain that we have. So that makes this problem a little bit simpler to solve here. But how do we find the length? What we are looking for in the problem asks us for the length of longest mountain in the array. That's what the problem asks us to do. And so once we find the peak, once we have the peak, like in this case here, we know that peak, let's put the positions here, 2, 3, 4, 5, 6. So we know the peak position to get the, so how to get the length? Well, the length is pretty simple. We know the length here, from here to here, because that's the up value, up at position I value, and we know from here to here, that's the down value. So it's just the sum of both plus 1 for the peak itself. And so the length is just up of I plus down of I plus 1. And so now we know that our algorithm needs to be like this. So we need to compute array up, and then after that we need to do another pass. So this would be from left to right. Compute all the length of the increasing subarrays in the array, and then we do the compute down, which would be from right to left, which would be just computing all the decreasing subarrays in the array, and then from there we can take max length, which is basically up I plus down I plus 1 for all elements I, so for all elements I such that, of course, we will have up I bigger than 0 and down I bigger than 0. This is basically means we are looking only for the peak elements, and for each peak we compute the length of the mountain it's peak of, right? And that's pretty much would be our answer. So let's see how we can solve this then. So the function that we want here is, let's define longest mountain, and we will get an array, right? So first we want to compute up, right? So we will initialize the array with 0 values, right? Because if it's decreasing the or equal, the value is 0. So we'll have 0, and then we'll have down, which would be also 0. And now we'll compute, we will do 1 here, the first step. So doing the first step, let's make this a comment, would be to go through the array from left to right. So we would have to do for in range of 1 to n. I'll explain why 1 here. What we want is if it's increasing, so the previous element is smaller than the next element. So if I minus 1 is smaller than ai, so we have something like this. And this would be ai minus 1, and this would be ai. So it's increasing. At that point, we want to say that it increased by 1, right? And so we would say that up of I is equal to up of I minus 1, right? The previous up of I for the element before that, plus 1. And so why am I using 1 here? Because if we use start from 0, then this would be a of minus 1, so it won't work. We want to start where we have a value to compare against. Because the first value, as we saw here with 8, is already 0, right? Because we initialize it to 0 here. And then now we'll do the second step, which is going from right to left. So to go from right to left, we can just do for I in range of, so we will need up to n minus 1. I will explain why n minus 1 again in a minute. But we want to reverse so that we can start from the last element and go to the, basically what we want is we want to start from this element here and then go to the left. And so for that, we want to check. So what we want is we want, if we contrast it with this going up, we want it to be going down. So we want something like this. And this would be I plus 1, and this would be a of I. So we want this one to be smaller, right? So what we want is for ai to be bigger than ai plus 1, and the other way to read it is a of I plus 1 to be smaller than the ai. So the last element would be smaller than the one before it, so that it will be decreasing. And now what this tells us is that the down at this position should be whatever down was at here, which is down of I plus 1, right? And so we just do similar thing here, where we say down of I is equal to down of I plus 1 plus 1. And now we are done with the last step. So only one thing to mention here is that I would need to do the last step, right? So which is getting the max length. So for all the peaks of the mountain. So that would be, we can do it quickly with a list comprehension, or we could, I'm going to first use something more clear. So yep, so let's just have a res value here that will hold the maximum length of the mountain. And so we'll go through for each index, and then we want to check if up I is bigger than 0 and down I is bigger than 0, which means we are in this case here where both are positive, so we are at a peak of a mountain. It's only in the peak that we have an increasing value bigger than 0 and decreasing value bigger than 0. And so only in that case that we want to check if that's the maximum length that we just found. So this would be res, and the length, as we said, is the up at position I plus down at position I, so this here plus this here plus 1 for the peak itself. And so that would be up of I plus down of I plus 1, and we would end up returning res here, right? And that's pretty much it for this solution. Yeah, so let's type this and then simplify it a little bit, maybe use a list comprehension here. But the main idea here is doing multiple passes, doing a first pass to the left to find a part of the solution, doing another pass backwards to find a second part, and then doing a final pass to find the final result. This trick is really useful to do multiple passes and at each pass collect some information. It allows us to solve problems in O of n time because, for example, if we try to find what's the time complexity for this solution, well, here we are doing one pass, so it's O of n, same thing here, O of n, and same thing here, O of n. So at most we'll do O of 3 multiplied by n, so time complexity is O of n. In terms of space, we are of course using these two arrays up and down, so we have O of n space. So maybe we could do better than O of n space, but time complexity here is really ideal, right? Okay, cool. So let's type this solution. Okay, so I written down here a solution for the problem that we just solved in the overview. And so same thing here, we have n, and then we have up and down arrays initialized to 0. We do the left pass or the pass forward to determine the length of the increasing subarrays at each point, and then we do the same thing for the decreasing one, going from right to left. And then at the end we found the peak elements by checking bigger than 0, so this here is the same as doing this. Just in Python it will return true if it's bigger than 0, so it's the same thing. And we find the peaks, and then from the peaks we get the length of the array of the mountain at that peak, subarray of the mountain at that peak, and we pick the max. So that's pretty much simple, and I have here a couple of test cases, so if I run them, they all pass. So this one, the length is 5, because this is the original example we took. This one, the length is, so we go up, and then we go down, and then we go up again, so the length is just 3. Here, there is no mountain, and so the length is 0. And so that's the main idea here. Now, we can simplify this a little bit, or at least use a list comprehension here. So the way to simplify this here to use a list comprehension is, instead of, so we can just comment this portion here, right? This last portion, and just return a list comprehension. So we will need to, since we check both up and down at each position, the same position at a time, we can just zip both and that will give us the same outcome. And from that, we want to find those that have up and down bigger than 0. And so what we are looking for is something like this, up and down in this iterator, right? That's basically the same as iterating this way. And we want here to take the sum and then add 1. So that's what we are doing here, right? With up I plus down I plus 1. But we want to take them only if they are both positive. So if u is bigger than 0 and d bigger than 0. Or we could do also the same thing here, because In Python, this is the same as checking bigger than 0. Same thing here. And from there, we want to take the max of all of them, right? And so we could just do max of this. But there is one problem. What if this list is empty? Then max will give us an error in Python. So what we need to is just prevent that by defaulting to 0, which is what the problem asks us to do in case the list is empty. And that's pretty much it. So let's run this. So that still passes. So one thing we can think of here is, can we do better than this solution here, which has open space? So can we do all of one here? And maybe also just do one pass instead of doing 3 passes like we did here. So for that, one important thing we can notice here is that, well, if we have a mountain going up and then it starts going down, as soon as it goes up here, it's the start of a new possible start of a new mountain. But we definitely know that this mountain has ended. So this is end of previous mountain, right? Because we were going down and then we went up, so it's no longer that previous mountain that we were at. So we can use this information here to kind of not need to use an array. So since the cause of the open space here is the up and down array, the goal we want to do now, what we want to do now is just make up and down just one variable and use that. And so from this here, what we can deduce is that we can set, if we use just one variable to keep track of the up value so far, right? And then when we reach here, well, both up and down will be 0, right? Because we are starting a new up, and we are ending the previous down. So both up and down are equal to 0 if we use variables. So the variables would be like the length of increasing subarray at I, right? And down would be, and I would be whatever position we are currently at when we are doing the for loop. Down, the same thing, length, similar thing of decreasing subarray at I, right? So we know that both are equal to 0 if either down, if down was positive, so we were going down, so that means down was positive. Because if down was equal to 0, then that means we were going up. And so continuing going up will not make them both equal to 0, right? We'll just increase up. And so only if down was bigger than 0, which means we were going down, and we just found it started going up, which means that the previous element is smaller than the next element, right? So if this is the case, then we know that we can initialize both, reset both back to 0. Or if we have a flat mountain, right? Let's say we were going down and we have flat mountain now, both elements are equal, right? Or we are going up and both elements are flat now. So or AI is equal to AI minus 1 is equal to AI, right? That means that, well, both should be 0 because we are neither going up, neither going down, and the length of the increasing subarray is at that point 0, and same thing for down, right? So with this, we know how to update the variables, and up would just increase if the previous element is smaller than the next element, and down will increase also if the previous element is bigger than the next element, right? And so using this info, we could just replace these 3 for loops with just one for loop, right? So let me actually do this in code in Python editor and show you, but the main information we'll use is this one here. And then we can update the variables in the same way, except we are no longer using the array, and we will update the res variable as we go along, right? So let's see how would that work. Okay, so let's see how we can do the optimization we just went through in the overview. And so to do that one, let's just create a quick solution here called 2. And we could, so just put back this, remove it here. And so what we are going to do here, maybe let me just put presentation, sorry, presentation mode. Okay, so what will happen here is we just do one loop, so we don't no longer need this one. And as I said, we just use variables for up and down to get the space down to O of 1. And we no longer need this loop since we will be doing updating res as we traverse the array. And so I'll use this something similar to this in a minute. And so here, as I said, that if the previous element is smaller than the next element, we are going to increase up. If it's bigger, we are going to increase down, right? Because that means we are going down. So that would be down here, and we could just use +1 like this. Same here, we could just use +1 like this. And as I said also, if the previous element is equal to the next element, that means we could just reset both up and down to 0 because we are no longer going up and we are no longer going down. And same thing, we will do the same thing. Basically, we'll reset both up and down if also we were going down, which means down is bigger than 0, and we are starting to go up, so we are no longer going down. So, and we are going up, start of going up, so it's also 0. So that would mean the previous element is smaller than the next element. We'll reset up and down, and that's pretty much it. We'll just need to update res here, so that would mean res is equal to the max of res. And same thing we're doing here, but we no longer have the array. We are currently at the position, and we are calculating for that position. So we can just do up plus down plus 1, but we will also need to do what we were doing before, which is checking that both are positive, because that means we have a peak. Otherwise, we don't have a peak, and we shouldn't calculate the mountain length because there is no mountain if that's the case. So we just need to check if up and down, which means both are positive, right? Here also we could just use down because in Python that would be the equivalent of bigger than 0. And we can run this and see if this passes. So okay, cool. Okay, so this still passes. One minor thing we can do here, since in Python when this returns true and you add it to a value, it will add 1, and if it returns false, it would add 0, right? So we could just directly add this, and if it's true, it will add 1. If it's false, it won't add anything, which is exactly what we were doing before. And then we could do the same thing for this here and just add the result of this Boolean value, which would be 1 if it's true and 0 if it's false. And that's pretty much it. If we run this again, still passes. And if we look at the time complexity, well, we have only one loop, so which is of n time here. We go through the array only once, so we have of n time, sorry. And then in terms of space, we are using only these variables, these 3 variables here, so it's of 1 space as well. And so we went from of n time of n space and 3 passes to of n time of 1 space and only 1 pass through the array. So this is a big improvement here. Okay, so another different solution that we can try to do here with a different idea completely, but I just wanted to show it here to have a different way of solving this kind of problem. So since if you kind of think about the solution we just did, the main thing we were interested in is finding the peak. So using the same idea of just finding the peak of all the mountains for all the subarrays, could just look up use the same idea of looking up the peaks. So let's say the array is something like this, where we have, let's say maybe the array, some values here, and we have a mountain like this, and the peak is here and goes down, and then we have some values, and maybe it goes up again, and then we have maybe it goes up right away here. So what you can see here is what we want to find is just the peaks, and for each peak we want to go all the way until we find this position, because maybe here it goes up or the values are equal, and same thing here, we want to go right until we find this position, and here we don't know what, maybe something else, but it's equal or it's going up, so that's where the mountain ends. And so for each peak we want to just go as left as possible until it's no longer part of the mountain, and we want to do the same thing for the right portion. And so what does finding a peak here means? So for AI, if this is position I, then the peak, the left element is smaller than it and the right element is smaller than it. So we can write this as it's the right element is smaller than it, right? And then the left element is also smaller than it. You can write it whichever way you want, but this kind of makes it clear that it's a peak. And so you could also write it like this. So the left element is smaller than it, and then the right element is also smaller than it, right? And so here actually this one is more clear that it's the peak. So the left element is smaller, the right element is smaller. The same way we have this visually here. And then if we find this, we can just initialize two things, left and right, and go all the way left with the while loop, and then go all the way right with the while loop until we find both the boundaries here, which are left and right, and then we can pick the max using a res variable here, and the length of the mountain that we find here is L plus, it's actually R minus L plus 1, right? And so the way to, let's write this down. So we would just need a res variable, right, equal to 0, and then we will need to traverse the array. So this will keep the maximum length of the mountain subarray, and then we'll do range of 1 to length of a minus 1. So why 1? Because we will be comparing against I minus 1, and so we want the, and so we want to be able to say I minus 1 and have that be a valid index. And the same thing for n minus 1, we want to be able to say I plus 1 and have that to be a valid index. And so here we will just look for the peaks, check if this I is a peak. So we do that by using this condition that we mentioned here. So that would be A of I minus 1 is smaller than, the element before it is smaller than it, and the element after it is also smaller than it. So if we find it, we initialize both the left and right to be at the peak, and then start expanding to the left and to the right to find both ends of the mountain, right? So what we will see is while L is bigger than 0, and it has to be still smaller, because the previous element has to be still smaller than the next element, so that we are still, we still have this side of the mountain. So that would be A of L minus 1, the previous element has to be smaller, right? So that this portion is ascending, is increasing, right? So if that's the case, then we want to go left to find the end of the left side of the mountain. So to do that, we'll do L minus 1. And we do a similar thing for R, except R is going to the right, so we need to check against the length of the array. So it's, while it's less than A, and I will use minus 1 because I'll be checking against R plus 1, right? Because if I don't use length of A minus 1, I will end up with N, which doesn't, which that index doesn't exist, right? And so, and for the right side of the mountain, I need it to be decreasing. So the previous element has to be bigger than the next element, right? So what this means here is I will check that A of R, the previous element, has to be bigger than the next element. that's the condition of being descending. And so if that's the case, then that means I need to go right. Okay, so that would mean r plus 1. And then once I have the value of the left and the right, I could just check if that's the maximum length of the array, if this is the maximum, the mountain that has the maximum length. And so I check max against res, and to get the length I would just do right minus left plus 1, right? That's how we can find this length here. And then I could just return res at that point, when I'm done with the for loop, of course. So it should be here. And that's pretty much it. And of course, in terms of time here, we will traverse. So even though we will go all the way here until we find this, for the next I, we will still try here, but we'll find that it's not a peak and we will advance, but we will still check. So it's not as good as the O(n) solution that we found before, but it's still a different way to solve it. And we are not using extra space here, so it's O(1) space. Okay, so let's run this solution and see if it works correctly. Okay, so I typed the solution that we just saw in the overview here. So we just traverse the array, look for a peak. We can also do this like the left element is smaller than the peak, and the right element is also smaller than the peak. So we could do it this way as well. And then we try to find both ends of the mountain, so the left side and the right side. So for the left side, we keep checking while L is bigger than 0, which means we haven't reached the end, right? Because the last position we will count it anyway, and then we will go and check against if the left element, the previous element, is smaller than it, then that means we are still in a mountain because the left side is still increasing. And then for the right side, so here we are doing bigger than 0, so that L minus 1 is always a valid index. And then for the right, as long as we haven't reached the end, and again here we do minus 1 so that L plus 1 is a valid index. And so we check, and for L, as long as we haven't reached the end and the previous element, which is AR, is bigger than the next element, that means we are still going down. And so we increase the right side, right? And then we pick the maximum. We pick the length of the mountain, which is the right side minus the left side plus 1, and we check if that's the maximum length so far or not. If it is, it will be set to it, and then we return at the end res. And so let's check if this passes the test cases. Okay, so test cases still pass, and so this solution is also pretty intuitive because we just look for the peaks and then extend on the left and the right side to find the mountain length, and that's pretty much it for this solution. Yeah, so that's it for this problem. We went through several iterations and 2 different solutions, and yeah, so that's it for this problem. Thanks for watching, and see you on the next one. Bye.